everyone. In this lesson, we're going to take a look at some polyatomic ions and how we would draw structures for covalent compounds that have a charge, as well as covalent compounds that will form multiple bonds, so double bonds or triple bonds, rather than just the single bonds that we've been talking about so far. So let's start by talking about polyatomic ions. So first of all, let's look at this word. So poly means many, atomic means atom. And ions, this is going to be a molecule or an atom that has a charge. So here we're looking at a molecule that has many atoms that also has a charge. So these are going to be covalently bonded molecules that have a charge, which means they're covalently bonded, but some electrons have either been added from the environment or some electrons have been lost to the environment in order to make that compound more stable. So when we go through and do this, we're going to use the same general rules as we used for making regular covalent compounds, except this time we need to add or subtract electrons based on the charge that we see for the molecule. So let's do a couple examples here. The first example, this is hydroxide, and you'll notice that these are all printed on the back side of your periodic table. We're going to be using these a lot more in our next unit, but for now we're just going to be taking a look at how they're bonded. So here I have hydroxide, which is OH with a -1 charge. So I'm going to start by counting up the total number of electrons involved in this molecule. So I know from my first oxygen, or from that oxygen, I have 6 valence electrons based on its location on the periodic table, plus the 1 valence electron from hydrogen. But this -1 charge tells me that there's an extra negatively charged particle in the compound. So that's going to add 1 additional electron to my count. So instead of there being 7 electrons, this molecule is going to have 8 electrons involved in the bonding. So when I go to draw this, I only have 2 atoms, so I'm going to start by single bonding them. So I have oxygen bonded to hydrogen, and now I'm going to start placing my electrons, my lone pairs of electrons, around my atoms. I know that hydrogen, because it can only have 2 electrons maximum, this bond already gives it those 2 electrons. So hydrogen can't have any lone pairs around it. So far there's 2 electrons drawn in my structure. So 2, 3, 4, 5, 6, 7, 8. Now I'm going to go ahead and put brackets around my molecule to indicate that this is a polyatomic ion, and give that charge in the upper right hand corner. So there is my correct structure for hydroxide. Next, let's look at ammonium. So ammonium is NH4 plus 1. So my nitrogen, based on its location on the periodic table, has 5 valence electrons plus the valence electrons from my 4 hydrogens. So 1, 2, 3, 4. Now I notice that this molecule has a +1 charge, which means that we've lost an electron to the environment because there's an extra positively charged particle in this compound. So instead of adding an extra electron, I'm going to subtract 1 electron here from this total. So here, instead of there being 9 electrons, there are going to be 8 electrons. So now let's go ahead and draw this. Nitrogen has the most bonding sites. So I'm going to go ahead and put nitrogen in the middle, and I'm going to bond those 4 hydrogens to each side to start. So I have 1 hydrogen, 2 hydrogens, 3 hydrogens, 4 hydrogens. So let's take a look at my electron count. There's 2, 4, 6, 8. So my structure is done here. Now I just need to put brackets around and write my charge +1. So that's how I would draw the polyatomic ion for ammonium. Now let's take a look at how we would determine whether a molecule is going to have single bonds, all single bonds versus some double bonds versus some triple bonds. So when we draw these, the number of lines in between atoms is what's going to tell you how many bonds are present. So 1 line between atoms, like here, that's a single bond. That's indicating 1 pair of electrons that's being shared. 2 lines, there's a double bond. That means 2 pairs of electrons are shared. And a triple bond, there's going to be 3 lines. That's indicating that there are 3 pairs of electrons being shared. So here's how we would go about drawing out these molecules that would have double and triple bonds. So we're going to use the same steps as we were using with our molecules with single bonds. There's just going to be one extra step added. So we're going to use carbon dioxide, CO2, as our example molecule here. So first we're going to calculate the total valence electrons that are being used in this molecule. So for carbon dioxide, carbon has 4 valence electrons plus 6 from each oxygen. So that gives me a total of 16 electrons that are involved in this molecule. So step 1, check. Step 2, arrange the atoms with single bonds around the central atom. So my central atom in this case is going to be carbon. So I'm going to put carbon in the middle, and I'm going to go ahead and single bond my oxygens to either side of my carbon so that my molecule is nice and symmetrical here. All right, check. Now I'm going to place the extra electrons to complete octets. I'm going to start with the outer atoms first before moving to my inner atom. So far I have 4 electrons placed because of those 2 bonds. So I'm going to go ahead and start adding 2, 4, 6, 8, 10, 12, 14, 16. Okay, so now I notice I'm out of electrons. This is all the electrons I have to work with. And I notice that each of my outer oxygens have their complete octet, but my carbon in the middle only has 4 valence electrons at this point. It has 2 from each of these bonds. So that's a problem. So what I'm going to do is I'm going to start transferring some electrons around. So here in my this is where that 4th step is going to come into play. So now I'm going to shift lone pairs of electrons in order to create double bonds or triple bonds so that I'm satisfying the octet rule. So essentially what I'm going to do is I'm going to take the lone pairs of electrons that the oxygen has, and I'm going to shift them to create bonds, extra bonds between the carbon and the oxygen. That will give carbon extra electrons, but it won't remove any from the oxygens themselves because now they're just sharing extras. So first I'm going to go ahead and take these 2 electrons from the oxygen. I'm going to bump them in here, and I'm going to create a double bond in between this carbon and oxygen. So these electrons got shifted away. So now notice carbon has 2, 4, 6 valence electrons now. So I know that I'm going to have to do this one more time. It's always best to try to make your molecule symmetrical. That's going to be the most stable configuration. So we're going to go ahead and go over to this other oxygen. I'm going to take one of its lone pairs. I'm going to shift it in here and create a double bond as well. So now those electrons shifted over. So now this oxygen has, hold on, let me change my color. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That's perfect. Now my oxygen on the other side, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And now carbon has 2, 4, 6, 8 from those double bonds on either side. So I'm going to go ahead and redraw this. When you are doing this, guys, please don't leave your molecule looking like this with stuff crossed out and everywhere. Rewrite your molecule so that it looks presentable. So I have carbon in the middle, double bonded on either side, 2 oxygens, and those oxygens each have 2 lone pairs. So there's my final molecule. Okay, so like I said in the last slide, you're going to try to make your molecules symmetrical. That's not always possible. In CO2 it was, but in chemistry, there are going to be situations in which our molecules are not symmetrical. They're slightly less stable that way, but those molecules do exist in nature. And what we call those alternate structures, we call them resonance structures. So this is what happens when there are more than one possible valid Lewis dot structures for a particular molecule. So here's our CO2. This center one, this is what we drew on the last slide. So we made it nice and symmetrical, but we could have technically had a triple bond on one side and a single bond on the other, that would have given us the same, that would have completed the octets the same way. Or we could have had a triple bond on the left oxygen and a single bond on the right. That still would have completed that octet for carbon. And that's still technically correct, even though they're slightly less stable. They're less stable, but they are possible. If you were to do any of these three on a test, I would give you credit, because those are all possible configurations for CO2. So there's going to be some molecules that we see where you may have a double bond only on one molecule rather than on multiple. So always try, if you can, go for making a symmetrical molecule, but if you can't, it's okay. And even if you do something like this and it's not symmetrical, then I'm not going to mark you off for it, because it is a possible configuration.